Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and process. In last couple of classes, we have discussed about the glass forming ability based on two different aspects. One is the topology of the short range order, which was discussed by several scientists, and the other one was empirical relations. The empirical relations has been developed based on some of the characteristic temperature like glass transition temperature, crystallization temperature, liquidus temperature and so on. And those equations we have seen are very much valid in order to represent the glass forming ability. And today we will continue that discussion and we would like to see that how different physical properties are correlated with the glass forming ability of the alloy. So, along this line we find out these physical properties like the minimum molar volume and the viscosity of the liquid is also important in order to explain a good or bad glass forming ability of a designed alloy. And there are also some other parameters people or scientists have correlated. Those are enthalpy of vacancy formation, let us say the local ordering. Ordering means we are talking about not long range order, the ordering inside short range order. Short range order means basically less than 2 nanometer in size, and also some other parameter like fragility parameter. And today we will discuss what are they, what is the fragility, what we really mean by the viscosity of a undercooled liquid and so on. So, in case of a minimum molar volume, there are some equation that came out and it says that the misfit energy is important. So, in a liquid the misfit energy and the atomic volume of the isothermal compressibility of this constituent element is somehow very much important. What does it mean? That a critical composition in case of a binary alloy, if we think about a binary metallic glass, there the decrease in the atomic volume is the highest, at which it is also expected to have the highest viscosity. So, you can see that these relations are very much similar and correlated to the one which we had discussed in the last class with the atomic mismatch. So, if we think about x b, which is the concentration of the solid concentration of B element, and let us say V a and V b are the atomic volume, then we can represent that x b, which is the minimum or the critical solid concentration required in order to form a glass. So, psi a and b, they are basically isothermal compressibilities. Now, there are also another one very major aspect, the physical properties that one should think about, that is basically the viscosity, because we understood that the viscosity of a liquid continuously decreases, and when it reaches to 10 to the power 12 Pascal per second or greater than 12 or 13 Pascal per second, and then it basically give you the glass. Okay. So, it is basically the solid viscosity. So, a best glass forming alloy will always show a higher liquid viscosity, almost an order of magnitude higher than the ores glass former. And also the best glass forming alloy show the smallest volume change upon crystallization. Okay. So, the ores glass former always show a larger volume change. So, if you see the plot of specific volume versus temperature, we will understand that what is the meaning of the excess volume. Okay. So, the viscosity and correspondingly small free volume in the liquid at the melting temperature contribute significantly to improve the glass forming ability. However, these understanding require some mathematical expression, and the Vogel, Fusser, Tammann, they basically describe this like Arrhenius type of equation, where the viscosity at a given temperature is basically the high temperature limit of the viscosity, and d star here is referred to a fragility parameter, okay, and T naught is referred to a VFT temperature. So, these two are appear to be constant for a given alloy. Okay. So, it says that at any given temperature, the higher the viscosity of an alloy will always show you a higher glass forming ability. And to understand this, what we need to do, we need to look at what are the different viscosity values of a good glass former and a worse glass former, and we need to understand that. Please have a look at the left hand side figure. Here it is a normalized temperature. It says if we increase the temperature from a glass transition temperature, this is basically Tg, and we are going towards the melting temperature. So, T is increasing here, okay. T is increasing here. So, here is the Tg. When T is the Tg, then it is has a value of 1. So, here is basically the glass transition has happened, and above glass transition we are measuring the viscosity of the supercooled liquid, okay. And then we are plotting here the viscosity versus the normalized temperature, and this is let us say the viscosity change with temperature of some polymer of some pure metal. This is the pure metal which is a ores glass former, okay. And now this one is vitriol, which is one of the best glass former in metallic system, and these square bubbles are the silicon dioxide, which is one of the best glass possible in an oxide system, okay. So, you see that the best glass former always show a viscosity level which is much higher at any given normalized temperature. So, the viscosity is very high here, and the viscosity of the pure metal is low here, or the viscosity decreases very abruptly in case of a ores glass forming alloys or material. Okay. So, we can categorize this side of the plot as a strong glass former, which will depict a higher value of D, and here are the fragile or ores glass former. So, here this fragile terminology does not mean it is a mechanical fragility, okay. This is a kinetic fragility we are talking about. So, here this fragility parameter D star provides an index of the stability of the glass. So, here one thing is very much interesting. You see that we are measuring the viscosity of the supercooled liquid, and we are describing the stability of the glass, which really happen below the glass transition temperature. We transform from the supercooled liquid to a glass. So, these two are very much interlinked, and the D star usually has a value of 5 to 100. So, let us say higher the value, the higher or stronger the glass, and T naught is a constant which is related to a calorimetric glass transition. So, T g is basically the calorimetric glass transition, and definitely the eta 0 is the high temperature viscosity, which has somewhat value of 10 to the power minus 5. So, the viscosity appears to be very much important. The viscosity of the undercooled liquid is very much important to illustrate the glass forming ability. Now, there are several other parameter has been discussed and told to link with the glass forming ability, like the enthalpy of vacancy formation. What it said that the measurement of vacancy formation in a glass can be done using simple electrical resistivity measurement, okay. And the glass forming ability will increase in case when the enthalpy of vacancy formation, the enthalpy of mixing and the configuration, the entropy will decreases. Okay. So, definitely the stability of the glass will increase and also the glass forming ability will also increase. What I want to mean that if you introduce a defect, okay. So, so the vacancy is a defect and then definitely we will get a different configuration, okay. And then by using that configuration we can decrease this value. Now, in some cases it has been observed that the local ordering in the short range order is also linked with a better glass forming ability. In some cases it has been observed that the chemical short range order is also important. What I want to mean that I have two different type of atoms which is making that short range order, and so whether a preferred chemistry is required in that short range order to give the stability. Now, let us say a particular type of short range order in terms of structure, icosahedral structure of the short range order which has been observed, let us say in case of a binary copper hafnium glass, is also gives us a better stability and better glass forming ability. So, these are some of the other parameter which appears to be important in some of the glass forming alloy system. Also, let us say Professor Angel, who basically mostly done research on this viscosity and strong and fragile liquid, and he classified this idea of strong and fragile glass forming liquid. And he classified these two different type of liquid in one case which has a strong glass former, means higher glass forming ability, and poor glass forming ability. So, the strong liquid with a very high viscosity and the fragile liquids are very marginal glass former, that we have already talked. And so, we can think about the glass forming ability of a complex function of the fragility and TRG, that is the reduced glass transition temperature, and the Tx, because we have seen that TRG is equal to Tg by TL. So, Tx, TRG, these are all these empirical relation came out, and we now introduce another term, that is the fragility based on the viscosity. So, the fragility means that a strong or a fragile glass former and how easy glass formation could be provided. So, here the fragility provides a measure of the sensitivity of the structure or the short range order or the cluster we are talking about. So, the physical significance of fragility gives you the sensitivity of a structure of a liquid with the temperature changes. Okay. So, if the structure changes very easily or kinetically it is more favored, then it is a very poor glass forming alloy. Okay. Because in the earlier plot we have seen that same situation. Once again I would like to show you the earlier plot. So, here also this is the same, that a poor glass forming alloy has a very fast change in the viscosity, means the structure of that short range order changes very fast, okay, in the glass forming, where this is a more stable glass. Now, here in this case Professor Angel introduced a fragility index parameter which is very similar like D star. Okay. So, in this particular case he told that the change of the temperature dependent relaxation time, which can be measured directly using differential scanning calorimeter, and the glass transition temperature with change in the temperature could be classified and can be measured of a fragility index, and from there we can directly say whether the glass is a better glass forming alloy or a poor glass forming alloy, like the fragility parameter or the fragility index we have discussed earlier. Now, there are definitely some other parameter including the mechanical alloying. So, many of the scientists they have prepared glassy alloys by mechanical alloying or let us say ball milling. In that case, what is understandable that we introduce defect by severe plastic deformation. Okay. So, we generate a high amount of lattice strain. What we want to mean, we start with a powder and then we mechanically alloy them, so that A and B, two different type of powder can mix with each other and make a solid solution out of it. So, that is the mechanical alloying, and in that particular case the heavy deformation that is experienced by the powder particle introduce some crystal defect, and once we introduce a defect, this means that there is some free energy related with that defect, and this defect raise the free energy of the crystalline phase, and sometimes the whole free energy may go above of that hypothetical of the amorphous phase. So, the amorphous phase becomes stable when the free energy of the defect and the crystal and their summation is basically higher than the amorphous phase. Okay. However, that this G c, that is corresponding to the crystalline lattice, and G d is the free energy due to defect, and G a is the amorphous phase. Okay. And if that amorphous phase shows some glass transition, we definitely call them as a glassy material or glassy alloys. And so far we have completed the discussion on the glass forming ability, and now we need to discuss about the phase transformation in the glassy alloys. The phase transformation means we have discussed about the TTT diagram and how a TTT diagram looks like. So, in a TTT diagram we think about a temperature and time, and here this is the crystal and here this is the T liquid, and we basically try to bypass the crystallization event, and if T g is sufficient we can form a glass. However, we can again increase the temperature, we will definitely go through a T g event and then there is a T x. Okay. So, this glass to crystal, this transformation is also a phase transformation, and we are talking about that crystallization event. Or it may be also that during cooling itself the liquid transform into two different liquid, that is also possible. Yes. So, in a glass forming melt or glass forming alloy, this kind of phase transformation is possible. When we think about crystallization, a crystallization means the crystallization may occur in a bulk volume or the crystallization may occur in a surface. Okay. And definitely when it occurs inside a bulk volume, we can think about a heterogeneous nucleation or a homogeneous nucleation. Okay. However, during cooling itself, if there is at all any liquid phase separation, then we can think about a spinodal type of decomposition which may be linked with a homogeneous, or maybe when a glass transform into crystal, then that glass may separate out into two different glassy phase, and this is also a phase separation before formation of a crystalline phase. So, these are the possibilities what we can think about in a phase transformation in a glassy alloys. Now, let us have a look at if there is a crystallization, what we can evaluate out of a crystallization event. So, this is a glass, the thermogram of a glass, and you see here a T g and here is the T x. Now, interestingly here you can see two another peaks, which basically means that this is T x 1, this is T x 2 and this is T x 3. So, there are three different crystallization event goes on inside a glass. So, it is not mandatory to have only one. Okay. So, there may be three different event goes on. However, we can measure the peak temperature of the event and we can use the Johnson-Mel-Abrahami equation in order to find out the activation energy required for crystallization. So, this is a mathematically measurements, and using DSC we simply put basically this log of beta by T p. Here beta is basically let us say the heating rate, and Q is the activation energy which we can get from the slope of the curve. So, from here this is a constant, the Johnson-Bell-Abrahami constant, A is a constant, and we can directly say what is the activation energy of crystallization 1, what is the activation energy of crystallization event 2, or let us say what is the activation energy of crystallization process 3. So, here was a glass and here is the crystal where it could be a several crystallization event, and we will be discussing these issues in the next slides. So, overall this crystallization process can be classified into 3 different types. So, people have observed that if we start with a glass, then the glass may transform into a single crystalline phase. Now, think about that I have a glass and I have a single crystalline phase. So, there is no need of the change of the chemistry of the glass, because the same composition evolve in the crystalline phase. Now, if the glass transform into 2 different crystals simultaneously together, then these 2 crystal whatever has been appeared inside the glass during heating. So, there must be a very large driving force, and you can see the parallel growth of those crystals, and here this is the only one type of crystalline phase is present. Okay. Even though there are some dark, and these are due to the contrast and orientation contrast. However, there could be a primary crystallization. So, these are the 3 major types. So, in case of primary crystallization, a glass basically changes its composition to glass 2 and another crystalline phase will appear. So, this is the primary crystallization. What is interesting here, you must look at that when a glass 2 appear, then definitely there is a need of the change in the chemistry of the glassy phase, and there must be a phase to be separated. Okay. So, this is a primary crystallization along with a phase separation. So, here this is the glassy phase along with some crystalline phase, and we can think about the thermodynamics of such event, and we can take an example which is a very common matte glass. So, matte glass is iron boron alloy, and here we have shown you the free energy curve of the glassy phase. Okay. And now, let us have a look at that if I take case 1. So, I start with a glass, from a glass it simply without any change in the chemistry of the glassy phase, I get a crystalline phase which is alpha iron, and so it is a polymorphous crystallization. This is case 1, whereas I can also may have where alpha iron is basically solid solution, that is why there is a continuation of this free energy curve. And now, if I have created a simply intermetallic phase, then in case of intermetallic you see this is case 4 where a glassy phase transform into Fe3b. So, this is also a polymorphous crystallization. However, in case of 3 and 5, so in case of 3 and 5, so if I start with such a composition and then crystallize it, then I will have a chance of getting alpha iron plus Fe3b. Okay. So, this is in case 3, or maybe I can also have that alpha iron, or I will have Fe2b. Okay. So, these are the eutectic crystallization. So, both the phase will appear in case of 5. Okay. And now, the primary crystallization will appear in case of 2, because I start with this composition and the same glass will have a different composition, right. So, here when there is a decrease in the free energy. So, I will have one phase which is alpha iron, and I will create a glass which has a different composition than the starting glass, and this is called as a primary crystallization. Now, I may also have a annealing event which is the structural relaxation, and in that particular case a sub Tg annealing is required. a sub-TJ annealing gives us that how much relaxed volume we have created. So, a relaxed glass always have a higher density than the as solidified glass. There are example of such, and we can see the density difference. By relaxation phenomena means if we heat up a glass, then inside the glass the excess free volume will release. So, this is called as a structural relaxation. So, in that particular process we can also have a chance of increasing the density of the glass. So, this is the density of the relaxed glass and this is the density of the as solidified glass, and you can see as we increase the relaxation, the density is also increasing. Now, I have magnified here the glass transition event of a thermogram of a glass transition event, and so here this is the Cp in the y axis and here is the temperature. So, from here you see if I pre-anneal a glass, let us say 600 K or let us say 450 K or 400 K. So, after annealing, if I again reheat, so let us say the initial plot was like that and I have annealed it close to Tg, I cool it down, again I reheat the same. Then initially the glass shows such a glass transition, but after annealing the relaxation, after annealing means after relaxation it follows this line. Okay. So, this is the enthalpy which is related with the relaxation, which is exothermic in nature, and therefore, we can see that if a relaxed glass and a as annealed glass will not follow the same path. So, a relaxed glass will follow this path than a annealed glass. So, how much we have relaxed a glassy structure can be visualized from the Cp curve. Now, this is a case of a phase separation. I have shown you the plots of different thermograms. So, these are for different alloys, and you can see that it is also possible to see two different glass transition in a same glass. A two different glass transition simplifies that there must be two different glassy phase. So, this is one glass transition temperature, this is another glass transition temperature. Even though the crystallization started here, but here there is a second crystallization event followed by another glass transition. So, this is another questions come to the mind, that whether these kind of glasses, how they have appeared in the liquid. So, one can think about the classical way of understanding a phase separation in a solid. In a solid solution, here there is a sphenodal, and if you look at the free energy curve, then definitely here if it is the composition of the average composition, and then there is always a chance that there is a decrease of the free energy, and we can get two different region with two different composition. Okay. And this is a automatic process by which we can go to the two different composition. Okay. So, I can also have a glass where the glass, if we provide some extra thermal energy, then the glass will dissociate into two different composition. So, in a solid state itself, the glass can be, there will be a phase separation. So, this is one of the idea that came because of such kind of event that people find out. Now, the phase separation can also happen in the undercooled liquid during solidification itself. So, let us say I may have created in a undercooled liquid a a zirconium rich or let us say a lanthanum. This is a lanthanum, zirconium, aluminum, copper, nickel system we are talking about. So, during cooling itself, the liquid phase separates into two different region which is schematically shown here. So, this was the initial liquid and then there are some other region appear and then two different region appear, two different chemistry, okay, and then ultimately these two regions solidified into a single glass. Okay. And so, definitely I will have two different phase and two different phase means two different glass transition temperature. So, overall the microstructure, if you look at the solidified microstructure has this kind of phenomena. Okay. And if we do X-ray diffraction, a normal, a conventional X-ray diffraction of a glass show you a single hump. Okay. And in case of such kind of two phase glasses, instead of a single hump we will see two hump which is appear here. So, two different hump is corresponding to a two different phase in the amorphous region. So, these things makes a more relevance to the subject and we try to summarize what we have discussed so far. So, in case of a relaxed glass, we can think about a phase separation into glass 1 and glass 2, where this glass 1 may undergo some sort of crystallization, let us say primary crystallization or let us say polymorphous or eutectic crystallization, okay, or maybe glass 2 also go for such kind of phenomena. Maybe we can again start with a such a relaxed glass where there are two glasses where we get a mixture of crystalline phases through polymorphous or eutectic mode. However, there may be supercooled liquid and we may produce a solid solution or intermetallic that I have shown you in case of a iron boron mate glass, and we may have created a solute rich phases. So, this solute rich glass may undergo some sort of polymorphous or eutectic crystallization, or maybe we can go for a mixture of crystalline phases plus eutectic. So, these are so many different possibilities like a single crystalline phase by polymorphous or crystallization. So, when we think about a crystallization or a phase transformation in a glass, not only crystallization is important, but also phase separation is important. So, here we are talking about phase separation means different in their chemical short range order. Thank you very much. We will discuss the other properties of metallic glasses in the next classes.